Okay, so first of all, I would like to thank also the organizer for this invitation, and it was really a pleasure to be here. And now I will talk about monitoring fault structure, but actually I changed a little bit my mind, and because of the previous talks, and I will start by some basic aspects, maybe, because we are here for something that is training also. So, and then I will speak about fault at the moment. And so, sorry, you do not hear me? Okay, let's. Here, better? Okay, thank you. So I will talk about ambient noise seismology, and I will not start by telling you what it is. So just to remind you that my talk will be in this context, basically. And so what we know is, as you already know, that we can retrieve in the Fourier domain what is the imaginary part of the green function, so the green function for positive and negative time, in the form of a correlation. And okay, you know that, but I just want to recall what are the conditions for this relation to hold simply directly. And there are some conditions. In the case where the field has been fully randomized by multiple scattering, we will be in the situation close to equipartition, and in that case, it should work completely. And it should work completely means that we have to believe in the mathematics. Meaning that you can retrieve everything, every detail of the green function in principle, you can retrieve. Of course, it's very difficult to find a field that has been fully randomized. So it's not the case, especially not with the noise. And if the noise results from a uniform distribution of source in the volume, in that case, again, we have a mathematical theorem. But of course, it's not the reality of our observation. We have not an even distribution, a uniform distribution of source. And then we have approximation. Approximation to representation theorem that allow to study and use the case where you have a uniform distribution of source on the boundary, for example. But it's already an approximation. And also, you can play with these different approximations and see how the physical things work if you make this analogy with the time reversal mirror. So we have this background, and now we have to play with the reality. So, and I will just start to be positive. That is that actually it works very well in terms of data produced by this noise correlation. It has been used a lot for different aspects of imaging, and so we start from this point. It works well for imaging, and it's useful. But we have some constraints. Now, what we are interested in is to do seismic velocity temporal changes. So, in that case, we want to find the change in the medium. And I just remind you that we are expecting slight change, because the very big change we already know. And if you have a major change of velocity by 50% in a wide region, of course, we already know. So we are looking for something more subtle that could be related to the issue that has been discussed in the previous talk, like damage, deformation, water change in the water content, and so on. So how can we use the noise to do that? This is an example of correlation during a long period of time, here, 6 years, and you have the correlation. The things I would like you to notice is the fact that if we are around the 0 time of correlation, so we have the positive time, the negative time, when we are in this region, we see very large variation of the correlation. And this means that these correlations are actually, at this time, are very sensitive to the change in the noise. For example, you see the seasonal changes very well on this figure. Interestingly, if we look at the left part, the coda, of this correlation function, apparently it looks much more stable. And this is what we see on this simple seismogram. So how can we understand why we observe such changes in the correlation, that is in the direct wave reconstructed by the correlation? So I come to relatively old stuff, but just to tell you, we can make an experiment. We have a lot of data coming from exploration configuration, where you have thousands of seismometers and thousands of sources. We took a situation like this one. We consider two stations here, and we take a ring of sources around. And remember, we have all the records in this system. And what we can do simply is to select in the seismogram let's say the first part to start with, the direct wave. So this is the envelope of the seismogram. We take the direct wave and we use all the sources and obtain this uniform distribution of sources that is plotted here as the intensity as a function of the angle. So it's a polar plot of the intensity of the sources of the noise. And if we have a perfect uniform distribution, it works very well. That is that we can compute the variation of the travel time with respect to the true grid function that we have measured in this case, and we found that it is 0, so it's good, we can believe into the theoretical work. But of course, we can play with the amplitude. We can play with the amplitude and decide that we will add a factor to the sources here, the record from these sources as a function of the angle with respect to the strike. And we can be, for example, in the strongest case, create a distribution of intensity like this one. But we can create all the possible cases in between. So this is an extremely anisotropic distribution of noise source with a minimum in the direction of the two functions. We can do the same, measure the travel time as a function with respect to the true green function, and look at the value of this error. And you see that there is an error, and there is a bias. And the bias, in a case like this one, is as large as 2%. That is large, in a sense. In some cases of application for imaging in the shallow structure, it's not so large. But let's say, keep in mind 2%. And we have this evolution. The more anisotropic is the noise field, the strongest is the bias. We can write a little theory for that and get this expression here that is fitting very well our observation. So we have this effect here in which we see the difference between the isotopic case, so perfect reconstruction in terms of time, and an error that appears when the field is anisotropic, and the error is inversely proportional to the travel time. It is also directly governed by the frequency, so inversely proportional to the square of the frequency, and everything is governed by the two terms here, B0 and the second derivative of B being the intensity, the azimuthal intensity, and the second derivative. So we have a rationale to understand these errors. And of course, it's not enough for our application, because if you change this noise a bit, actually you will create a change in the bias, and this is what you will measure in the dt over t as a function of time. So it's a problem. But again, let's be positive. This is a quite negative perspective because we use only the direct wave here. If we redo the same experiment, exactly the same experiment, but now we use the coda wave of the original record. And we try to reconstruct, again, we look at the direct waves that we reconstruct. Of course, what is the effect of the scattering? It is to completely smooth the distribution of intensity in the various directions and tends to promote an isotropic field locally. And then in that case, when we do the same application, we retrieve the travel time of the green function with a much better accuracy. Meaning that you see it's not perfect. You see that it's not perfect. There is still something that is unacceptable in a way for us. But you see that it's much better. And our data are always mixed between the ballistic wave and the scattered wave that are present always. So in that case, we see that anyway it's better because scattering provides the diversity of incidence. And there is no clear bias. Meaning that now, talking about tomography, with an error at this level, I think in most of the case, this error is actually smaller than the residue of your inversion. And so it should not be too much of a problem to have this type of difficulty. And this is what we have seen with the development of the tomography. But now there is another part of the seismogram that we can try to reconstruct and compare with the observation. And this is here now a numerical experiment in exactly the same situation, in which now the medium is strongly scattering, at least scattering. So the meaning that now we are not discussing the ballistic wave, but the waves that are multiply scattered, and you see the snapshot of the field that show you the direct wave and the scattering that is quite strong. And we can compute for this situation the cross-correlation of the field produced in this situation here of anisotropy, and compare the correlation here, you see with the noise, with the green function that is plotted below. And in fact, you see that it's a very good reconstruction when we see it like that. But you know that we are looking for very small variation in the medium. We make a precise measurement of the difference between the two signals. And what we found is this. This is the dt over t in red, if you want, as a function of the time in this seismogram. What we see that there is a bias at the beginning for the direct wave, and the bias we compute is actually smaller than the theory prediction because of the presence of the scattering that is helping. But very rapidly, you see that the dt over t reach a very small value that does not evolve with time. And if you consider this type of measurement here, with this very strong anisotropy and so on, we found that, and we make a little theory for the scattered wave for that, and the fluctuation we expect are in the order of 10 to the minus 4, with no accumulation of delay with lapse time. So why it is so different? It's because in one case you look at the path as something that is only geometrical, so the issue is the orientation of the path between the two stations and the field. And now we look at the coda wave, and the coda wave cannot be seen like that. The coda wave corresponds to a very large set of almost random walk into the medium. And in the large part of this set, there is no possible bias because the scatterers are frozen in our medium. Meaning that actually we are just playing onto the position of the first scatterer. And so in dt over t, that ends up to produce very small variation. Okay, because in one case it's purely geometric, in the other case it's controlled by the position of the scatterer. So, conclusion, from the beginning it's good to use the Coda wave because it's more stable than the direct wave. And so, okay, let's go to practice. So you all know this figure, and we can discuss it a lot, and there is a lot of other spectacular applications in volcano and slide hydrology and so on. And I would like to discuss more what is behind for you. You see the velocity drop, it has been discussed, the velocity drop for San Simeon earthquake, for the Parkville earthquake. You have the drop, you have the relaxation, and we can discuss the fact the relaxation here and here seems different, for example, so there are maybe more than simply the local response of a material. You see that here you can see the correlation with the tremor activity. Here it's the trend of the GPS in the region. So maybe there are other type of time scale that we observe in these things that not only the relaxation of the shallow layer. But what did we do with this measurement here? It's what Céline explained. We use this idea of measuring the increase of the delay along the seismogram, and we measure this delay here, and we can take the slope of this delay, this delta t over t, that is equal to minus dV over v, and at the end we plot minus dV over v. And this is what we do, and it has been, this is what you all call the Coda wave interferometry, and actually, just to give credit to the old worker, Poupinet, Ellsworth, and others, in 1984, used exactly this technique for doublets of earthquakes. That is, earthquakes that repeat themselves exactly at the same place, and that you can use for measuring the variation of velocity. But just a point, in their paper, they insisted a lot on the fact that what is critical is to observe this linear trend. So, and this linear trend is a form of proof that these delays are really associated with a change of velocity everywhere in the medium. And so it's something we should keep in mind. So, when we use this type of techniques, first of all, is there evidences only at the surface? It is one of the issues that we heard in the last days. I just want to show you rapidly example of changes at depth. Very rapidly. Just this one, this case is in a mine. We are in a deep mine, and in this mine here, you have at about 1 point something kilometer depth, you have a series of seismometers that are working for safety reasons that has been explained this morning by Ian. When they actually create a new tunnel, they blast and they excavate, and after you have the seismicity. And for safety reasons, they wait the time needed for the seismicity to disappear before to restart to work. So it's why we have this seismometer. But we can use this seismometer to measure dV over V and try to have an idea of what is happening at depth at the time of this blast. So let me try to show you this. This is a little movie. So here we will see the velocity in 3D with the network, and the time is passing here, and this is the time of the blast, and this is smoothed by the fact that we use a window to measure in this application. And so, if we look at this small movie, if I find a way to, yes, here, you see that there are some fluctuation, very clear, and then at the time of a blast, there is a large drop of velocity in the medium. A large drop of velocity with a relaxation afterward, and actually the medium that reach another stable situation with zone of positive and negative increase of velocity. So here we see the what we call the phase dynamics, the effect of the strong shaking, the slow dynamics, the relaxation effect, and a change of baseline that is due to the static stress change. So we can just compare these things here. It's just a slide view. The instantaneous velocity drop is seen here. That you have a region where occurred the change of velocity, the region where the aftershock occurred, but you have also static velocity change that is represented here in side view and in plane view, and that you can compare with the elastic stress modeling done by the engineer of the mine that show you the region of compression and dilatation that correspond to positive and negative change of the velocity. So at least at 1.5 kilometers of depth, we can observe what is observed in the laboratory. So now, if we consider another scale completely different, the effect of the Tohoku earthquake in Japan, and here we are in a frequency range that is written somewhere, but yes, here, 1 to 7 seconds. What it is what we observe after, you see, typically 3 months after the earthquake. What is observed in the laboratory. So now, if we consider another scale completely different, the effect of the Tohoku earthquake in Japan, and here we are in a frequency range that is written somewhere, but yes, here, 1 to 7 seconds. What it is what we observe after, you see, typically 3 months after the earthquake. So there is a change that occurs everywhere in the northern Japan, and the distribution is centered in this region here. If we compare with the PGV, the strong motion, you see that the strongest effect corresponds to the region of the largest PGV. So that indicates that at this frequency, we are measuring something that seems to be controlled by the strong motion from the Tohoku earthquake. If you consider now much larger period, that is much deeper, you see that there is a difference in the distribution of the change, meaning that it's not simply a surface effect that is projected at depth by the technique we use. And now you can compare this with the dilatation caused by the Tohoku earthquake. So in these two cases, you see that it seems that there are different sources of changes as a function of depth, and that there are even deep changes. And just to show you this in 1 second, here you see different measurements that are based on seismometer, the INET network, and by tilt meters that are used as long period seismometers. And you see that we found different time history as a function of the depth. You see that for the long period, the immediate effect of the earthquake is very limited, and that the delay is starting to increase after. And so you see that not only the spatial distribution is different from depth to surface, but also the time history. And we try to understand these things, and you observe something very strange, is that you have the Toku earthquake, the largest aftershock here, the relaxation, and there is still a decrease. And we try to understand why. And this decrease is not associated with seismicity, it's not associated with precipitation. Actually, we look at all the possible possibility, and we did not find really. The only thing that seems to appear is that after the earthquake, there is something starting at depth that is, in fact, you know, here also you see that the relaxation stops and is propagating toward the surface. And this effect is the strongest in the region of the volcanic range, and we interpreted it as the sign of the transfer of fluids from the deeper crust to the surface. Okay. So now we come back to our first approximation. Our first approximation here is to get directly the dV over V from an analysis, looking for that, and the typical technique for that is the stretching method. Now, physically, it's very simple to realize that if you have a receiver and source that are close here, you have a finite size region at around the surface here, and at a point, you have the extent of solar wave. So here, the waves are sampled only the region with the change. And so the dt over t is a constant. But of course, if you wait a bit, what you found is that when the wave propagates out of this region of change, of course, the accumulation of delay is smaller, and the dt over t is changing with time. So already it's asked a question, is that when you measure directly dV over V, you are measuring this, or you are measuring the average here, or this value here. So you see that quantitatively, you are lost. So there is no way to get away from that than trying to find a way to take care of the lateral variation of the change of velocity. And to do that, there is the possibility to write a form of inversion based on a linear formulation. A linear formulation in which the delta t that you observe at a certain time tau in the correlation between R1 and R2 can be written at the form of an integral of the distribution of dV over V times a certain kernel that relies these two parameters. And this sensitivity, exactly what is relating the travel time to the spatial distribution, can be calculated by measuring the time the particle pass in each zone of the medium when going from the source to the receiver in a given time. So it's computed at a given time. Okay? And so this kernel can be used to reconstruct the distribution of the change. And I think I have no magical solution for this problem, but I would like to convince you that this is a problem and that we have really to try to solve it if we want to have quantitative evaluation of this change. Okay, the details of the subsurface are not known, and actually to perform this differential imaging, we will rely on statistical models of heterogeneity and solution of the radiative transfer equation that will be a perfect tool to approach this problem. So why we need to rely to the radiative transfer equation that is, you remember from the, of course you remember from the class of Ludovic that this is an equation for the specific intensity, that is the intensity of the field resolved in a given direction. And this is very important to keep this in mind because the field is intrinsically anisotropic. Even in the coda, even in the CODA, there is, even when you start to have a good fit with the diffusion approximation, the diffusion is actually describing the energy flowing from the source outside. And so there is a direction of propagation. And so it's important to keep this information in mind. And it's also very important for the kernel itself. So let me try to explain in one word these things. That is how we could compute this kernel, that is understanding how the change that is occurring here for a source that is here, a virtual source here, recorded at this station here. And what is represented here is the problem of propagation between this point and this point, and between this point and this one, or the reciprocal from this one to this one. And as you see, at a given time, the specific intensity produced by the source is very anisotropic. And if you want to know what is the effect of this point, you should take the direction of the propagation that I took here, so the specific intensity in this direction, and ask you, I want to know how this energy will be transported here. And for that, you use the radiative transfer, the green function of the radiative transfer, to look at this direction. And so here is the reverse problem. So you see that what is important is what is in the opposite direction of propagation here, just because it's the reverse propagation. And so, and of course, if you have extremely directive, just to understand, if you imagine it's extremely directive, it's a ballistic wave. Here, you change the velocity here, and here you have a ballistic wave that is plotted like that. You take a direction, and you find that the only direction that is counting is this one, while in that one there is no contribution in this direction. You see, I have not the impression to be very clear. But at least you understand that what is counting is not only what is the energy you have at a point, but the distribution of energy as a function of the angle, and the possibility to be propagated back, to the receiver. So it's why the example of saying, imagine a case of the almost ballistic wave here, you will get something like that, completely in this direction. This one will be completely in this direction, and you see that when you take the negative part of this direction, you get 0. And of course, it's intuitive. If you change the velocity here for the ballistic wave, you will never see it. Okay? So this effect is very important to take into account and allow to write a form of the kernel in a form where you have the intensity between the point of interest and the receiver, computed at a time t minus t prime in the direction that is minus n prime, multiplied by the incident intensity, that is r prime t prime n prime r0, and then you will have to integrate this over all the t prime. So you will get always the arrival at time t, and over all the directions. So in other words, the natural way to compute the kernel is to use the radiative transfer equation. Okay, and so if you do that, you obtain a form of kernel, and the form of kernel in the homogeneous case will be something like that we can see here. That is, at the beginning, you have seen that it was the kernel of the ballistic wave that is included in the solution. And then there is a long evolution that is very, very simple, where you see that there is a strong sensitivity around around the source and the receiver. And you obtain a quantitative value of that. So we can use this to make maps and obtain results that could be maybe more quantitative than what we can do without this type of effort. So let me show you an example, because we discuss a lot of shallow region. Here it's a space-time monitoring of groundwater fluctuation, and in that case, we use these types of kernel to analyze the change in the Los Angeles basin with the standard California seismic network. And this is data that are available. Okay, you can get this data, and you have here the hydrological view of the basin here, and some names that are present in this map. So what we will do is to look at this region in the long term, but to try to have a spatial distribution, and because of that, we can expect to have reasonable values of the change. So this is the, oh, does not work as it should. Okay, just a little problem, I'm sorry. You know, from time to time, these things appear. Let me just do that. Tubes. This could be okay. Yes. So we have here maps at different frequency that we obtain of the dV over V, and you see that at different frequency, that is at different depths, the distribution are different. And this is also known from the structure of the basin. And this is, as a comparison, the ISTerre variation during this period. So you see that maybe something interesting for us seismologists is that the ISTerre is completely integrating the depth, and that he actually integrated these different information. And there is something very important here, is that when you look at the deep part of the basin, where the reserves of water are, you obtain this map. And on this map, you see that it seems that there is this line that plays a part. And this line is not coming from the geological map, but maybe for us it's a sign. It's the sign that maybe we are in the Anthropocene now, because our maps are controlled by things like that, that is the boundary between the Orange County and the Los Angeles County. And the water management is different on the two sides, and you see it very well on the deep reserve of the basin. So if we can do this type of things, we could be useful, but also we obtain quantitative measurement, and you see here the evolution of the average velocity during a period from 2000 to 2021. And you see very well also there that the seismic velocity tends to increase with time, increase with the drought, and you see very well the seasonal effect. You see the contribution of the years with strong precipitation, and it gives some information, but very clearly you see the trend in general. What is interesting is that if we consider this region here, we have some measurement of the hydraulic head in borehole, and of course we have everywhere an evaluation of this dV over V with time, even when we have no station that are collocated, and we can compare how it fits. And you see that the dV over V, in this case, in most of the time, not always, I agree, but most of the time, is well correlated with the waterhead. So it's really a good indication. And also, what is interesting to see is that in this region, it's very flat. So with respect to the discussion we have yesterday about what we can do about all the problem of climate and drought and everything, maybe here there is a part of an indication that in the place where there is a very precise and clever management of water, they manage actually on 21 years, you see, that the waterhead is almost at the same level. And the seismic velocity too. It's not true in the other part of the basin. Okay, so now I was supposed to speak about faults. So let's go to the faults rapidly. This is seismic fault imaging and passive seismic fault imaging. The first things we can do, of course, is to image directly the fault for the velocity. And this is an example of in Southern California where using the 150 pairs of station, we can make slices of velocity, S-wave velocity maps. And you have here the San Andreas fault and here the San Jacinto fault. And you see that the faults at depth are associated with low velocities, but it's not a general statement. It's really clear for the San Andreas fault, much less to the San Jacinto, for example, the San Jacinto that is here. And so you see that we have indication of the fact that the characteristic of the medium around the fault is very variable and not systematic either. So now let's try to consider another fault where we know not so much, but the North Anatolian fault. So we are now in Turkey. Here, you see, it's the North Anatolian fault where the Izmit and Lice earthquake occurred. And there is this array called DANA that has been installed by British colleagues a few years ago. And this is a sketch of the structure we have in the region. And what we did is that we used the correlation to measure the amplitude, the intensity of the coda in different regions. The intensity of the coda is a function of the distance for different times. And what appears is that we cannot fit the data with a uniform distribution of scattering parameters. And so I make the story short, but to fit this data, what we observe is that we need to add a narrow ice scattering zone along the northern branch of the North Anatolian fault here. So this is what you need to fit this data. And so this is an indication that the scattering could be very variable around the fault. This is a form of statistical perspective. We can try to image directly, also with passive imaging. And this is what we have done here. And here you have two sections, south-north section. And I realized that I did not put the section, but they are here and here. And what we did is that we use this array and we compute the cross correlation, and we work in typical configuration of body wave imaging. So in that case, we do not consider the surface wave at all. We use this matricial approach that is using the extreme redundance of information that we have, because we can build a matrix with all the response between all these traces here. So from this big matrix, we can use techniques that are based on beamforming, backpropagation, and so on. And the most important, and not the most, but very important, is to find a way to correct the aberration, to correct for the change of velocity. And this can be done by iterative techniques that was originally developed for medical imaging. And so we use this technique and we obtain this type of section here, where we see that actually this characterization now just of the, mostly of the scatterer, show you here the Sakarya zone that is in the south here, when you find a very typical image for continental crust with the upper crust that is almost transparent and the reflective lower crust. And this is the mole that has been obtained by receiver function. And then just north of the southern North Anatolian here, you see that there is a change in the characteristic of the crust. This is the Armutlu block, and the Armutlu block is a old structure. Actually, it's the intraported suture that is full of mantle material and very complex structure. And then here it is the region of the North Anatolian, the northern branch of the North Anatolian fault, where we see that we observe scattering. On another place, we see that the Armutlu block is diminishing in a way. This is the sliver, in fact, and we have this region of scattering that is actually going at depth, and we see even some indication of the presence of the shear zone in the mantle. So the conclusion is that this fault from this passive imaging exhibit a concentration of scattering along the fault due to the very long period of deformation and damage and rupture that leads to this region where you have tens and tens of kilometers of slip that has accumulated. So, what is the impact of having this observation? We can make a numerical test to see what we can expect for the future. We have the North Anatolian fault or the Sandras represented by a band with stronger scattering property, in a medium with less scattering. We consider only a very small array, because here we have only 9 stations, and we expect to detect what could be a form of precursory deformation, that is a velocity change, a velocity drop in the fault zone in this region. And we would like just to check if it's possible to image a thing like that. And we use the kernel I described before, and we use the kernel for the model with uniform scattering, and this is what we found. We found that the station that is just on the anomaly is sensitive to the anomaly, and for the rest, there is a spread of the information that is in different places, but also on the different stations. So you could be, again, optimistic or pessimistic. So you can say that maybe we would be happy to be able to find a thing like that, but on the other hand, for a synthetic test, it's not very good. So why it's not good enough? The reason is that we neglected the non-uniformity of the scattering. So now we can redo the test, and this time we will introduce a fault zone with a high scattering band. We will compute this kernel and question, is this kernel different from the other? So there is a guess is that, you know, diffusion, everything is smooth, and so on. But you will see it's not true. If you consider this kernel, here, look, At the beginning, it's the sensitivity is in the ballistic wave between the station. But when the time is passing, you will see something very special, that the interaction with the fault. And you observe these patterns that appear that are absolutely non-intuitive, I believe, and that actually are really a dominant, a very important parameter, I mean, feature of this image. You see, when the coda waves start to interact with the fault, the kernel changes completely. And the kernel is very strong away from the fault, not inside. It's not intuitive. You see, there is no high sensitivity inside. The sensitivity is projected outside. And it's due to this story of what is important, and what is important is related to the direction of propagation of the waves. So we built this kernel, and so we can redo our inversion. We take the inversion again, but this time we use the kernel with the non-uniform scattering properties. And it's much better. Because you see, we have a concentration of the change at the right place. There is very little smearing of information around the station. So you see that at a point, if we want to do proper imaging, we have to have a very good initial model of scattering. And this is something that we do not have very often. And then the next issue that I did not discuss is the depth dependence of our observation. And for that, we rely a lot on direct simulation that has been done in a paper by Anno Berman and others. And it was based a bit on brutal force, that is complete simulation of 3D elastic half space, in which actually the synthetics are computed with spectral element method, and then layers are defined, and in each layer there is a change of velocity, and then recomputation of everything. Okay, so it was a lot of effort that I did to get this numerical simulation. The conclusion is that when you look at the apparent change, this is what she called epsilon here, apparent change as a function of depth for a given frequency, a given time, you see that the observation is the blue line here, and the body wave contribution is here. And so you see that the observation is a mix between the surface wave sensitivity, that is actually dominant on all this part and disappearing at depth, and the body wave. And using this argument, she did this picture in which we have a partition coefficient. A partition coefficient that is just telling us that the change is due to a partition term applied to the sensitivity of the body wave and the sensitivity of the surface wave. And what is found is that this is the red, the surface wave. At the beginning, the surface waves are clearly dominating. And for what I saw in the publication is what people keep in mind, and use the surface wave to compute the depth dependence. And of course, with time, it's the part of the surface wave is diminishing, and at large time, the body wave are dominating. And there is, you see, a crossing at something like 7 mean free time. 7 mean free time mean that in practice of the application we we have seen recently, we are in this range here. Because of the signal-to-noise ratio in the correlation, it's difficult to be much far. So, no problem. That means that we were not too bad in using the surface wave kernel. But the problem is that we have no real theory for that, and it's a problem. And so we try to understand how it works and to try to see if we can retrieve with a simple model this property and this partition of the sensitivity as a function of time, partition between the surface wave and the body wave. And so with Andres Barraras, who was a PhD student and the chairman, we found a way to have a simple model in which we have the Hall space and a surface wave. So we have a scalar problem with surface wave. So actually, you know, for the acoustic case, there is no surface wave. So this is done by using a model in which there is a special condition at the surface that is no more free, but it's called the Robin condition. And in that case, you could have a model in which you have a scalar Helmholtz equation for the body wave and the propagation of a surface wave at the surface, really at the surface. And so, so I have no time, of course, but just to tell you that we can compute different terms. We can compute the surface wave. We found that there is an exponential decay with depth. We can compute everything, and then we can write now a coupled radiative transfer equation that is here, and that is an evolution of what Ludovic has shown the other day. It's still an equation onto the specific intensity, but specific intensity for the surface wave and for the body wave with some coupling term, and some coupling term with a property that was not completely expected, but there is a depth-dependent scattering mean-free path that appears in this story between the body wave and the surface wave. And now we have the surface, actually the wavelength, the surface wave wavelength, that is a parameter in the equation because it controls the decay of the surface wave. So I will just tell you a word about the conclusion of this analysis. And one of the interesting effects is to look at the partitioning. And the partitioning between the P and the body and surface wave. At the surface, we are thinking about this idea of equipartition. So if we wait sufficiently long, we expect to be, first of all, in a regime that is well described by the diffusion equation, and then asymptotically going into isotropy and equipartition. But when we look at this equipartition here, for different position of source, shallow or deep, we obtain this curve, and we see that it's written at the surface that we expect that there is an equipartition of the body wave and surface wave in this coupling, and that the dynamics is relatively similar to what we know for the elastic case between P and S, that after, let's say, tenths of time, mean-free time, it is partitioned, the energy is well partitioned. And the specificity here that is, I think, interesting to discuss is that we can also look at the global energy. That is, in your field, you inject a certain energy, and then you look at the ratio in this total energy, the ratio between the two modes, between the body wave and the surface wave. And this is what is plotted in two cases, one shallow, one deep, and now it's the total energy. So you see the partition with the stability is verified locally, but globally, the ratio has no constant asymptotics. And this is a big difference with the equipartition for P and S, for example, in the homogeneous space, because here we have this decay of the ratio of surface wave to body wave, and this decay has the form of the square root of the time. And this is due to the fact that if you imagine very simply how the fields are evolving, you see that the support of the waves are growing with time. But in the case of the body wave, you are looking at a 3D growing, so like alpha sphere, while the surface wave has a certain penetration, time just a circle. And so there is a dimensionality effect that you can see here, and that actually is something that was not fully expected, that there is no global equipartition of the modes. So we use this model to try to revisit an computation, and it's a difficult problem because we have to retrieve the different times, and you have two different ways of thinking. When you look at the waves that arrive at a point at a certain time, you can consider the time he has passed during this long path of scattered wave as a body wave or as a surface wave. And then there is another problem. It's a problem of detection. What are you detected? Are you detected a surface wave or a body wave? And so you see that with this in mind, you should work a bit to write the things. And I feel that Ludovic is already. So we redo the computation, and we found a figure that is very similar to what we have seen from Anne, and even we compute the time partition coefficients she proposed, and this is what we get on one case, where you see that we have retrieved the dynamics that was in this fully numerical simulation. And the last point that we can learn from the theoretical study is that if you look at the time partition coefficient for the body wave, and you consider different value of LS, that is the penetration depth, that is globally, let's say, scaling with the wavelength, and the mean free path of the body wave, and you compute all this combination. That gives you a series of curves, but you see that the curves corresponding to either the triangle or the continuous line are exactly the same. Each time, the ratio between the mean free path and the penetration depth are the same. That means that the sensitivity of the system is completely controlled by this ratio. That is a good thing to know, and and of course we have to consider the fact that actually the two terms, but at least clearly LS is completely frequency dependent. But it's a good indication on how to choose the situation in which we are by just knowing an idea of the mean free path and of course the frequency you are using, from which you can easily retrieve the penetration of the surface wave. But this research should bring us toward a full 3D coupled kernel, hopefully in the next years, if you work well. So just my short conclusion. I tried to convince you that the measure of dt of t with scattered wave is useful, but the measure of dt of T because a lot of information are controlled in the nonlinear part of this function. That I try also to convince you that, of course, we have a lot of signal coming from the surface, but there are also clearly signal coming from the deep part of the Earth. And to advance, we need to have a good knowledge of the structure, velocity, and scattering. And we are very often missing the information about the scattering properties. And this is a problem. And if you want to be a step further, I mean, if we play the next step, we have to include the body wave and surface wave coupling in 3D. And I think this last year we had good advances on this point in different groups. So this is something that will be also part of the future of this field. And I will stop here. Thank you very much.